All right, welcome everyone. In this video, we are going to we are going to discuss the public key format introduced in BIP 340. When the Bitcoin during the inception of Bitcoin, a public key was encoded as a 64 byte. So both the x and y coordinates were encoded. But later in BIP 137, right? So what they did was they only encoded a single byte for the y-axis value. Why they did it? So for that, we have to take a look into the SECP26K1 specification. So this P is the prime number which is used for modular arithmetic. So whenever you are multiplying two numbers, you like it's not a regular integer multiplication. You are actually taking the modulus on this prime number P. So your favorite programming languages, you are using your favorite Bitcoin like SECP library. So anytime you do multiplication using that the scalar or the secret key defined in that, so internally it is taking modular using the modular arithmetic on this prime P. This is a general uh, elliptic equation, which is y square is equal to x cube plus ax plus b. For SECP26K1, a is chosen to be a 0. B is chosen to be a constant 7. So y square is equal to x cube plus 3 is the elliptic curve equation used in SECP256K1. And this G, capital G, is called the generator point. As you can see, the first byte is separated, and then we have 1 2 3 4 5 6 7 8, which is actually 4. So this like 8 characters. So 8, 16, 24, 32, 40, 48, 56, 64. So this actually, so there are like 64 characters that you can see, but internally when you are representing in byte format, that is actually 32 bytes, not 64 bytes. The reason being they are using hexadecimal encoding, so every character corresponds to 4 bits, not 8 bytes. Since a byte is 8 bit, so total we have 32 bytes. This number 02, what does it indicate? It indicates that we have this 32 byte is the x coordinate. So given if we substitute the value of this x coordinate into this equation, okay, so we have y square is equal to x cube plus 7, which is a number. So there will be always two solutions, right? Potentially possibly two solutions for y. Remember, this is not real numbers, so you don't take the square root. What you do is you take the quadratic residue for y. There is two possible solutions. Since p is a prime and it is an odd number, so 2 is the only even number which is a prime. Every other prime number which is greater than 2 is actually odd. So because of this property, and one of the quadratic residue will be an odd number and the another one will be an even number. So this 02 indicates that the y coordinate, right? So the value of the y coordinate is an even number. So we can ignore the quadratic residue. There are two possible solutions to this equation. If you plug in a single value for x, we can ignore the solution which is an odd number, and we only take the solution which is an even number. So the value of y is determined deterministically because of this single byte, because 02 indicates that we are only looking for even solution. If here it was given 03, we would be looking for odd solution. We will ignore the even solution. So this is how compressed form of the elliptic curve points were used till the introduction of BIP 340. In uncompressed form, G has, the prefix of the uncompressed form is 04. So both the x coordinate, it ends here, the x coordinate ends here, and the y coordinates are encoded. So total 65 bytes were used. And as you can see, the y coordinate ends with the value of 8, which indicates that the y coordinate is an even number. So both of these representations are equivalent. Okay, they are not equal in the literal sense. If you do byte comparison, of course they are not the same, but they are equivalent in the mathematical sense. The order of this group, right, this elliptic curve group, not this integer modulo group, the order of this elliptic curve group is n, which is this number. If you observe, you can deduce that this number n is actually less than this prime p. That's something to note. So what does this order n denotes? It denotes that if you multiply g n times, you will get the identity element of the elliptic curve, which is the point at infinity. If you want to do a deep dive on this, refer chapter 2 and 3 of Programming Bitcoin book by Jimmy Song. This is the specification, okay, which was used. But in this BIP 340, a 32 byte public key was introduced, which means y is derived implicitly. Okay, what does it even mean? So given an x, we saw that there could be two possible solutions for y, but they have came to a kind of a conclusion that we are only going to choose the positive y number. Okay, I mean, it doesn't exactly like work that way, because we are not finding the solution in that way. I will explain what do I mean by that. Okay, as we know, right, so imagine this is an elliptic curve. Okay, let's say this is the point P that we are interested in. The negative of that point P will have the same x-axis as point P, but same x-axis value, but the negative y-axis value. The negative y-axis value in the modular arithmetic, it means n minus y. So if y is odd, this n minus y will be even, because n is p minus y, not n minus y. Okay, this will be p minus y, because we know that this p is an odd number, right? So here it is. I mean, if it ends with a 1 bit, it is an odd number. All right, so p is an odd number and y is an odd number, so negative y will be an even number. If y is an even number, negative y will be an odd number. Okay, so they decided that we are only going to work with the points on the curve which has even y coordinate value. So we are going to ignore all the points on the curve which has odd coordinate y value. This has serious consequences. I mean, of course, this diagram only works when we work with real numbers. So this is only for illustration purposes. Okay, so that's a great answer by Peter Will in the Bitcoin Stack Exchange, I believe, that he explains why when we are using modular arithmetic, it is not possible to have a graph like this. I mean, if we can have a graph like this, then it's not very secure. Anyway, we cannot use that for cryptography. All right. Let's say, how do you, I mean, so after BIP 340, the way we generate the private key itself changed slightly. There is one more check. So imagine, right, so you are randomly selecting the private key. So imagine you have a random number generator, which I represent using RG. So this emits the private key. Okay, let's say yes. What we do is we compute s times g, which will be the public key. This public key, it has x and y coordinate value. Okay, what we do is, if y is odd, this implies we will choose negative s, which is p minus s, as the secret key. Okay, if y is even, we will choose s itself as a secret key, because the secret key gave a point in P which has even y coordinate value. This means we are going to potentially ignore half of the secret keys as well. Okay, we are only going to use like half of the secret key, and we are only going to use half of the elliptic curve points. Yeah, I mean, this is the kind of inconvenience for the programmers as well. Why do I say it as an inconvenience? Is this necessary? Are we saving so much in block space by removing a single byte? I don't think so. This requires, I mean, this addition, this does not improve any security guarantees. If you go and, I mean, I have published a video on the signature malleability and how BIP 340 Schnorr signature avoids signature malleability. See, what does signature malleability mean? So signature is this pair, okay, or comma, let's say yes. So this is a different yes than this yes, okay. So it's like in Schnorr signature, it's capital or whatever. You have this pair, right? In ECDSA, for the same R value, okay, n minus s, which is negative s, will also be a valid signature. So we have two valid signatures for a single transaction input, right? I mean, for an input in a transaction, potentially. Okay, so in SegWit, it is they fixed it by using lowest value, because only after that fix, lightning was able to, I mean, lightning protocol was able to, yeah, come, I mean, the lightning protocol, idea of lightning protocol arrived much earlier, but they had to wait till the segwit software to enable it in production. So in that, I have explained how Schnorr signature avoids signature malleability. In this video, I did not talk anything about public key encoding because that is irrelevant. So this uncompressed form of this uncompressed form 64 bytes, or this compressed form of 33 bytes, in both the situations, we can deterministically determine which public key that we are, I mean, which y value that we are interested in. So here, only after this check, okay, so at the secret key generation and at the random number generation. So remember, in the signature scheme, we need to have a secret key and a secret nonce value, right? And with the secret nonce value k, there is a corresponding capital R, which is k times g. So even when generating this capital R point, we have to check for the parity of R, whether the y-axis of this R is odd or even, and based on that, we have to choose the positive or the negative k value, because the R that we are going to send in the in the Schnorr signature. So in the Schnorr signature, we will send this pair where this R is there's a slight difference, right? So in this ECDSA, so this is, let me just write it clearly. So in this ECDSA format, so we will only send the x-axis value of this R. So let me just denote it as capital R X, right? But in the Schnorr signature, we need to send the complete this point R for verification. So we could have used this compressed 33 byte format to encode R. So that will be one extra byte. So this 32 byte implicit derivation of y saves one extra byte. Okay, just saves a single byte in the public key and in the capital R. So it saves 2 bytes right? It just saves 2 bytes for the Schnorr signature verification, right? That's it. Does this provide any additional security? I don't think so. It just, I mean, so this introduction means we cannot use a potential, or I mean, we cannot use half of the valid secret keys and half of the valid points in the elliptic curve. This adds confusion to the code base also. Now in the code base also, they have to add these checks, right, whenever they are generating the secret key and the corresponding point in the elliptic curve. Anyway, I have no idea how this thing affects the later protocol development. For example, there is this idea of music, right? Music is different from multi-signature. Music allows the signature aggregation, right? Signature aggregation and public key aggregation. That's why Schnorr signature is very important. Like the BIP 340 is very much required for the Bitcoin ecosystem, and it is very useful. It can potentially increase the privacy, save a lot of block space. But do we really have to save this 2 byte? That's my question. All right, I hope you enjoyed this. See you soon. Thank you for watching till the end.